The next topic, DC-DC converters, will be interesting. So that's what I am saying. I recommend you to use your computers rather than your mobiles. At least you can have an exposure of it. Uh, Soham Chakrabarti, you have logged in two systems, so you can choose any one. Yeah, thank you. You will have zoom option in your screen. So you can go to view and zoom to any extent that you want for. Okay. Did anyone completed this? So let us take 2 more minutes. The certificate will be given to the participants only if you have if you meet 75% of the total attendance. And is it just for 2 hours? Just spare your time, uh, just learn it and then leave. Okay, let us go to DC-DC converters. Is my voice fine or is it very low? Can anyone respond? Is my voice okay? Okay, okay. I mean, it's not too low, right? I'm using the computer speak mic. Okay, okay. Thank you, thank you. Then let's go to the next topic, that is DC-DC converters. So let us start with the basic converter of all, that is buck converter. See, this is the basic representation of a buck converter. As I said initially, you have a switch. You have a switch. Let me take the rotation. You have some source. You have a switch. And you have some load. By operating this switch at variable times, so some voltage is going to appear across this based on your time period. Based on your time period and duty cycle. That means on time to off time. This is on time. Based on time to the total time. You can say only till this part, not the entire thing. Till this part. So based on time, which you call it as duty cycle, which is T on to T off. Total time, TS, which is your switching time period. So if I have this average time moment, so some voltage is going to appear. If you just take its average based on your output voltage is actually dependent on this D and on your input. If my input is constant, if I'm going to vary this D, obviously my output voltage average value is going to change. But when can I get this average? if you have smooth current and if you have smooth voltage, by using these filters, you are going to attain your average current and your average voltage. Otherwise, if just switch is open and closed, you're going to appear voltage across the load for some time and it is not going to appear for some time. So what does this capacitor do? It's going to smoothen your voltage waveform, and this inductor is going to make your current smooth. So let us, when it comes to operation, it can be operated in two modes. One is when the switch is on, you're at, so you're going to apply we're going to apply when the switch is on. So a positive and negative potential is going to appear across this diode. So it will become reverse biased, and the entire circuit will be your voltage source, inductor, and your capacitance, the parallel combination of this capacitance and resistance. So this is your load. So when the switch is open, so because of in the steady state, initially inductor is going to charge with polarity positive and negative here. We all know that inductor does not allow sudden changes in current. So at a later stage, it is going to reverse its voltage polarities. That means it will have a positive and negative here. Because of large negative potential at this node, this diode is going to get shorted like this format, and the equivalent circuit will be only this one. So this diode is an equivalent representation. This is how you'll have two operating modes. By doing KVL and KCL operation, you will get your V naught, which is nothing but D times of VD, where D, as I said, it is the ratio of on time to off time. So on time to total time. Okay. Now I'm going to see this with respect to state variables. I just want to develop a state space equation from that. So I have two two passive elements here, the main filter elements, which is my inductor and my capacitor. So I'm going to choose these two as my state variables. If I can find these two, then it is easy for me to find any other one. I can find is input source voltage, and I can find load voltage, load current, everything, because these two are in parallel. Whatever VC of t, the same will be the V naught, and whatever V naught we have, if you know V naught by R, then you can find the current through the load. This is how we can find. So in this mode, okay. Let me make. The system is crying. Okay. So in this mode, if you apply KVL here, so it is like VDC plus voltage across this is nothing but L di by dt. If you take the inductance L, it is L di by dt and VC. So what are my state variables? IL and VC. So in order to form a state space equation, the derivative IL dot IL dot is equal to some form IL dot and VC dot. So it is stuck in 1 minute. Okay. So my state space format, as most of you know that This is how you'll write it. So you're going to write x dot in the form equal to some constant matrix or some matrix into x. So the same, it should be in derivative format. If x is IL, then x dot should be dIL by dt plus some constant matrix B into U. Here U is your input. In this case, VDC is my input. So if I apply KVL to this loop, I'll get minus VDC plus L dIL by dt, or I can write L dIL dot plus VC equal to 0. I want in this format like dL by dt is equal to, here dL by dt I have. So let me send everything on the right hand side. I'll get it like this. So minus 1 by L, here x2 is VC, whereas my U1 is VDC. So U1 is my VDC. Similarly, if you apply KCL at this node, what happens is IL is equal to this, you can say it IC, and I load, which is nothing but this VC by R. Instead of IL or I load, I can write it as VC by R because both are in parallel. What about IC? We know that IC is equal to C dVC by dt. I want dVC by dt. I want this variable. As I said, x2 dot is again my another state variable. VC dot is again my another state variable. For that, if you just apply KCL at this node and if you rearrange the terms, you'll get this equation. So this equation I'm saying, this is for KCL and this is for KVL. So now in the left hand side, you shouldn't have any derivative terms. You should have normal terms only. Sorry, in the right hand side. In the left hand side, you should have only the derivative terms. That too, a first order differential terms. If you don't have first order, if you have second order or any other order, then you have to adjust it. There are some state space methods that you can do manipulation for that. Like if any double dot is equivalent to, you can take it as some another variable x1. Sorry, x dot you can take it as x1. So x double dot. So x2 you can take it as x double dot. Then x2 is equal to x1 dot. Sorry, x2 dot is equal to x1 dot. And it's not annotating. I'll just explain the things here itself. So if you apply KCL here and KVL here, you'll get these equations. That means these two are my dIL by dt and dVC by dt. So you'll get this format. This is first when switch is on. So this is how my switch is on. So when my switch is off, this is shorted. I mean, only diode will come into picture for the load. And if you again apply KVL, here dVC by dt is not, sorry, VC is nothing but dL by dt. So that's why I'm having only this. But what happens across the inductor, you'll have a reverse one. You can see this. We will have reverse polarities during this case. But actually, you are going to consider the polarity of the current is unidirectional. For that, you're going to get a negative sign here. Because at the time of doing the analysis, you have to take only one directional. Then only you will get that analysis. If you do that, you will get this state space equation for off time. In order to perform any operations like any closed loop or whatever it is to assess the stability, whatever, I need state space format of one thing. Now I have two modes, when switch is on and when switch is off. So I got two modes here, which is not, so it's difficult for me to do the analysis. So what I do is I'm going to do average of this thing. That means I will take this matrix. This is for some time. This is for some time. Let us take, this is for time TS or DTS. What about this? This is for time 1 minus DTS. That means out of the total time, it is remaining time. T off is equal to TS minus T on. What is my T on? TS minus T on is nothing but DTS. So if you take the, you'll get this term. So instead of T off, so it is going to off for this time. It is going to operate for this time. So what I do here in the manipulations, I'm going to take the first matrix and I'll multiply with D, the second matrix and then I'll multiply with 1 minus T. So this is how I'll get the equation. If I do that, P A on into D plus A off into 1 minus T. This is how I'll get. Similarly, I'm going to take for B, if there are C, D matrix, whatever the state, whatever the output that you want, that you can take it as Y. Here, my B matrix is obtained like this. What happened to my state variable? This is my state variable equation, like X dot is equal to AX plus BU. Now, I'm going to take the same state variables as my output. So Y1 is nothing but my current, inductor current. Y2 is nothing but my capacitor voltage. It is not mandatory that you have to take two outputs. You can take one output itself. You can take Y2 as your V0. You can take it as V0 itself. You can take it as, instead of these two, you can take it only V0 is equal to 0, 1 into ILVC. You can take this itself. It's not mandatory that you have to take only one output or two outputs. The outputs is up to you. And both of these are independent of U1. Now let us do this analysis in the simulations. Let us compare this average space model with the existing MATLAB Simulink platform. Let's go here. SLX. Okay. I will do the analysis along with you. So I'll do some time. First, I'll explain. Then I will also do in parallel with you. Let me comment this. This is for boost converter. The timing I'm just making. So this is my buck converter, as you can see. So I have given some input voltage. This is my switch MOSFET. You can type MOSFET somewhere. If you can see that this is your MOSFET and diodes, the same circuit I have connected, whatever I have mentioned there. And this is my state space representation. There is something called state space. If you type state space, you'll get that. This is your state space representation. Now, what is my state space equations that we have? What about A, B, C, D? Here I have my A matrix, B matrix, C matrix, and D matrix. So those I have to enter here. What is my A? It is 0 minus 1 by LC and 1 by C. This one I'll give you as it is. Control C. I'm giving you A, B. I'm giving you A. So you can directly copy that and you can do Control C so that the execution time can be reduced. The next one is B. Control C. The next one is C. You can see that in chart box. The next one is D. See, when I mention column there, that means from then the next row is going to start. I have given space here. When you're copying the things properly, at least you don't need to do this simulation, at least do this one. I don't think it will take much time for it. It will take hardly minutes. So what I did it here is I have given the variables VDC and I have taken my inductor value as L, capacitance C. The same thing I have defined here. These are all different variables like L, C, and R are my variables. Okay. So I have connected the circuit. What I did is I'm going to compare this average state space model, whatever the average state space model that I have here, which is a function of duty cycle. See, this is a function of duty cycle. This average state space model I'm going to compare with the existing buck converter. Okay. So here, this is my inductor current coming from state space model. This is called mux, you can say, using, sorry, this is dmux. I have two outputs, right? As I have given two columns, definitely I'll get two state variables, or actually two outputs will come. I have considered my state variables themselves as my output. So I'll get two outputs here, which is my IL and VC that I have given using mux. I have given to some scope. Here I have generated I have connected the same simulating circuit and I just want to see how it is going to work. Let us see what values I have given in the callbacks initial. So let me, I think I have, for the time being, I'll just give you this one. This is with non-linearities. Control C, Control C, chat box. So I'm giving you the model properties also. You can copy that. So for duty cycle 0.5, we know that your V naught, V underscore naught, we know that V underscore naught equal to D times Vn. Actually, you can write in LaTeX format in this, in the latest MATLAB. So this is the LaTeX format. Okay. So this is your duty cycle. What about my input voltage? I have given 12 volt here. 12 volt I have given. 12 volt, create annotation. So for input 12 volt with duty cycle D.5, sorry, 0.25. I have given this is my duty cycle. So obviously, what is my V naught? It is equal to 0.25 times 12, which is nothing but 3 volt. So my output voltage or my voltage across the capacitance should be 3 volt. So let us check that. Let us do this one instead. As you can see that I'm going to operate this at some switching frequency. So I have operated at 5 kilohertz switching frequency, and I have just multiplied D because I have defined D in percent. It's not in percent, but they have asked pulse width in percent. This is a basic pulse generator. Make sure it is in time based, and you have to use simulation time. Amplitude 1. The second should be 1 by 5000. So you can simulate this itself. So this I'm going to tell you how we can do this. For this one, as you can see, this is actually, I'm going to compare the current of the inductor current, which is around 1 something. So inductor current is 1. But if you see the actual simulation of this, if you see this inductor current is having some ripple content. What about that? In average model, it is almost constant. You don't have any ripple here. So if I cannot find it ripple, what is the use of that? Actually, you don't need, if you see that average value of this ripple, it will have some value. But practically these two have to overlap, but they are not. I'll tell you why this difference come here. So it is something average, like you can say 0.9 to 0.7. On an average, it is going to operate at 0.8 somewhere here. So it is going to operate an average value somewhere. But if you see that actual inductor current, it is something 1. Why it is 1? I have taken my load resistance R as 3 ampere. Sorry, 3 ohm. I have taken my load resistance as 3 ohm. So if it is 3, and if my output voltage, what is that? Output voltage is also 3 volt average value. So this is average value. So obviously, if you don't consider on an cycle, current through this is 0. Current through the capacitance is 0. On an average cycle, voltage across the inductor is 0. Okay. So if you take its average current is 0. So obviously, if you make 3 by 3, your inductor current in average model, it will be 1 volt, 1 ampere. If you see here, it is going to be 1 ampere, the inductor current. What about your capacitor voltage? It will be around 3 volt. It is going to give the exact value because I have given VDC as 12 and I've just used the state space representation and I found this. But if you apply here, you have got a bit less. This is because you're going to use number circuit here. Because of this, even this on state resistance, you're going to have that. If I'm going to involve non-linear things also here, like if I'm going to consider that on-state resistance and that diode's equivalent drop and its equivalent resistance and resistance of this, parasitic resistance of this inductor, parasitic resistance of this capacitance, if I consider that, then I'm going to get both the models properly. I mean, both will have an exact overlap. These two will have an exact overlap. Let us check that whether we can get it or not. So I'll give you questions. Sir, whenever circuit simulation may fail, what are the boundaries? I don't know what are the boundaries. I've used a solver OD23T, and you can see that maximum step size at bottom right corner. You can see the maximum step size. I've used 1A minus 6, and I've used OD23T solver. So you can use the same thing and you can try. I don't know what about the boundaries here. You don't need any boundaries here. Actually, I am not getting the point what you said. Okay. See now, this is the comparison between this and your state space model. As I said, if I'm going to include the non-linearities, then how your system going to behave? Let us see that. Okay. So this is my state space representation. Now I'm going to consider the dynamics. I mean, it's not just an ideal MOSFET. It will have some, it is equivalent of some resistance during its on state. And this source also I'm considering with some on state resistance. There is a diode, and this inductor is not a pure inductor. It is going to have some resistance. I think I critical, C critical. That is for continuous conduction. Here I've used large values of capacitance and inductance. If you see that, even in chart itself, I mentioned now, the C is 22 microfarad and L is 2 millihenry. 2 millihenry is quite large. If I'm going to reduce the switching frequency, let us say that it is something 100. Let us say that it is something 100. Then you are going to get a very large ripple, and discontinuous conduction may be coming here. You'll have a lot of formulas of them. Because my switching frequency is quite low, the inductor and capacitor cannot do it for a long time. You have those formulas everywhere. Is my voice not there? Is it okay now? Am I audible? Okay, okay. Thank you. So it's audible. I was saying something. Yeah, the critical inductance and critical capacitance. Normally, we won't go for till critical inductance. We will consider the amount of ripple that we want. Suppose, let us go for the switching frequency as 1 by 5000. My system is very slow. Okay, so for this one, as you can see, it is going to have some ripple content. It is going to have some ripple content. If you either increase the switching frequency, let us see that. If I'm increasing switching frequency to 10, right? What happens to this ripple now? I think this is this is capacitance. This ripple content is going to reduce further. See, you can see the ripple content now. It is going to reduce. No one is going to bother about the critical capacitance. They bother about the ripple content. So my ripple, so among all, suppose what is your actual DC value? Suppose it is, assume that it is 2.4. If your actual DC value is 2.4, how much ripple you're going to allow? So what is your delta VC? This is your delta VC. This is your delta VC. So there are some formulas for this delta VC. You have to choose a specific allowed delta VC for your network. Maybe consider that it has to be 1 volt or 1 millivolt or 0.1 volt. It's up to your choice. I mean, for your network, if it is allowing 1 volt, then you can go for 1 volt. I mean, if it can attain, if it is very sensitive and you need to reduce the ripple content, yes, you can go for 1 millivolt also. But in order to reduce the ripple, either you have to increase the capacitance drastically or you have to go for higher switching frequency. What are the possibilities in the laboratory? Whatever the capacitances that are available in the market that you choose, and based on that, you're going to choose your switching frequency. But what some people do, if your network is large and you are using a microcontroller, in the microcontroller, it will have some clock frequency. If you are operating at very high frequencies and you have multiple PWM networks from that, then it cannot generate that high frequency with multiple networks, because you're going to deploy the program using C language. So C language is sequential. So as it is sequential, the entire clock frequency is going to split among them. For that, you have to compromise in switching frequency and you have to go for higher capacitance value. If this, if this lower ripple is your main requirement, if 1 millivolt is your main requirement, then you have to go for it. But generally, there is a trade-off between them. That means you are going to have the capacitance value and you are going to have some switching frequency. So you're going to have a trade-off between that and you're going to operate that. Okay. You can simply see anywhere in the, just Google it, you'll get that C value, delta C derivations. There are some NPTEL videos that explain the derivations also. And critical inductance, maybe for gate point of view, it is important. I mean, they used to ask, but in normal cases, it is not such a prominent one. They consider only the amount of ripple that is allowed in their system, and based on that, they're going to choose the capacitance or the switching frequency. Even it is the same in the case of inductance. Actually, based on inductance and ripple current allowed, they're going to choose this switching frequency. It's not based on capacitor, because the continuous current plays a, I mean, the ripple in the current plays a dominant role if you are going for cascaded DC-DC converters, like maybe dual active bridge converters and all. Okay, what I'm saying, yeah. So this is my basic DC-DC converter, and here I have the state space representation of a basic what do you call it? Basic DC-DC converter in ideal case. So this is what. So here I've got my DC-DC buck converter in ideal case. That means I have not considered the influence of parasitic elements across inductance and all. If you see here, my inductance is not pure. That means its quality factor is not infinite. What you can say the quality factor? It is actually the true power, what do you call, apparent power to real power, or you can say I square XL to, simply I'm just writing I square R. So if your resistance of that inductance is 0, then you can say that inductor is of very high quality and your quality factor will be very large. But in practically, you won't have infinite quality factors. They will definitely be associated with some RL. Similarly, the capacitance, you have to consider the dissipation factor, and based on that, you can find this RC. You can find this using that meters. You can find this using Q meter, or you can simply use a simple RL network that you have studied right in your BTech. There is something called like this. You might have studied a simple DC source in series with resistance and an inductor. If you can give that ammeter reading to DSO, it will show you that waveform, and you can find the time constant T, and you know this resistance. So from that, as you know, T, it is nothing but L by R. It is R is nothing but R plus RSC actually. So you have to consider that. And once you find this, you have to, you know, this R, you will get a relation between L and RSC. Based on that, you can find suppose you have to take another parts also. By taking these 2-3 instances, you can find L value and RSC value. You can use DSO in your system, I mean in your labs itself, to find the time constant. I mean L value and R value. You don't need LQ or meter. So For this nonlinearity, again, as you can see, there are two modes. One is this mode, the other one is this mode. Now, I mean, my diode is equivalent with some DC value with RD, and my source is not a simple ideal source. It will still, it's going to drop for something, like I'm going to consider it Rn. When MOSFET is on, its equivalent representation is a series on-state resistance. So I'm going to take it as RDS, inductance RL, and capacitance dissipation factor RC, and this is my load itself. So again, there are two possibilities. If you can see that equation in mode 1, in this mode 1, you have to apply KVL here. The same thing, you have to apply KVL and you have to apply KCL at this mode. By applying that KVL, you can see that Rn plus RDS, Rn plus RDS plus RL, Rn plus RDS plus RL, the entire current flowing through this is IL itself. So into IL plus LdI by dt. The voltage across the inductance is LdI by dt plus I need the drop across this. In order to know the current through this, I will subtract the load current from this. Or actually here I have applied KCL, not here. They have applied KCL to load. I mean, let me take this annotation. So I have applied KCL to this load. It is up to you where you want to apply the KVL. But KCL will be applied here because that is the only node we have. So it's like it is C dVc by dt, which is your IC. So in order to apply the KVL, it's Vn equal to this entire drop plus this drop plus this drop. So this drop, in order to find it, it is I load into R. What is my I load? It is actually IL. Here is my IL minus C dVc by dt. I can understand it's very complex because the notations are not proper. I don't have other alternatives. Actually, I can use presentation pen. No, it's not working. Okay. So again, I'm going to apply the KVL and KCL. I'll get these two equations. What I have to find in the left-hand side, so I'll just get these two equations. In the left-hand side, I should have my derivative forms of that equation. That should be a function of IL. This is entire IL and VC and input. So you should have an equation like this. So your x dot is actually a function of whatever x you have plus and g of u, whatever the inputs that you have. Here my x, I have two inputs, IL and VC. So this is my IL and this is my VC. This is my another state variable. Similarly, dVc by dt is also a function of IL and VC. So I have obtained this. So obtain this, consider duty cycle as D. As you know that in two different possibilities, like this is one during on time. During on time, the buck converter equivalent is like this. During off time, the buck converter equivalent is like this. Same, you're going to apply the KCL at this node on the KVL in any loop. So if you apply that, you'll get this. So as I have two state variable formats, I have to take averaging method. So consider duty cycle D. So if I multiply this equation with dt and the other equation with 1 minus dt, then I'll get two equations. So here you can see that notation. So these two I'm going to take average. So what is my LDI by dt? It is actually the sum of these two, where R1, R2 is equivalent of this. I mean, instead of taking this much large value, I'm just going to take one notation R1 and R2. So if you take similarly the capacitor voltage notation, my state space equation like dVc by dt is in this format for duty cycle on time. For duty cycle off time, this is my equation. So it's my equivalent dVc by dt format, which is again a function of IL and Vc, which are my state variables. So now I want to find the value of IL and Vc as a function of duty cycle. As you can see, dIL by dt and dVc by dt, I have obtained these equations. So these are my state space equations. So let us see that in simulations. So this is my ideal case representation. Right click, comment out. Now I'm going to consider the non-ideal case and comment. See now that resistance RDS I have considered. The on-state resistance, this you can ignore, you don't need to bother about that. And the diode on-state resistance is RD, forward voltage is VD. The inductor resistance is RL and L, and capacitance I have considered here. Again, now my state space equation is going to change. It is not just VDC now. I have another variable called diode voltage drop. If you can see, IL and VC are my state variables. See, this is my VC, this is my IL. These are my state variables. Then I know my input. Then what about this VD? Do I have to consider it as a constant or what? If it is a constant, where I have to include that? So again, this you can going to consider as a separate input to eliminate perplexity. So that is why I'm taking my diode drop as separate input and VDC as separate input using mux. I have given as input to this. As you can see, I have written the same equation, minus dR1 minus of 1 minus d into R2. This is my IL. If you see IL, if you take common from both of this, we write this on it. Just take this entire term. If you take IL common, you'll get minus d R1 minus 1 minus d into R2. This entire term. Okay. So this is how I'll get. So this entire term, I have to place it in IL. You can see here, this entire term, I have placed it in IL form. And space I have given, see, I have given some space. Then what is my VC? I mean, the second variable is minus R by R plus RC. So this is what I have written, minus R by R plus RC. And in the next column, now your state variable VC will come. So R by R plus RC and minus 1 by R plus RC will be in picture. So this is how it is. What about my B and C? B is like 1 is in one of that. What is your input? D you have. So I'm going to give D. You have another input also, minus 1 minus D. Like you have to write this in this format. Write it. So you'll write D minus 1 minus D. Here I don't have any VC or any VD or VDC. So it will be 0, 0 here. This in multiplication with V input and VD. If you multiply, see, D into Vn minus 1 minus D into Vd. So D into Vn minus 1 minus D into Vd. If you see that for Vc, you don't have any of these elements. So you just take 0, 0. Now it is like this is the B matrix. As you have two inputs, it is going to have, as you have two state variables and you have two inputs, obviously your B matrix will become 2 by 2. What about your C? C is same because I'm going to consider my output is as my state variables. I mean my state variables themselves as my output. So it is 1001. My D is like this. Let me copy that. Control C. I'm giving it in your chat box. Control V. Control V. See, the average model is not recommended to see the waveform structure. Only this simulators, whatever the simulators that MATLAB is giving, whatever the simulating blocks that MATLAB is giving, it is good to find that structures because they are going to use some solvers like ODE, trapezoidal, or some Euler's methods, backward Euler's, something like that they are going to use to solve this equation to get the output. But in case, if I use the average model, see what is my simulation time, 0.05. The same thing I'm going to compare. Now you'll see a different thing here. See my inductor current, it's actually keep on rising. It is not stopped. What about my capacitor voltage? It is still 0. I'm expecting like it may come at a later stage. Let me take 1 second. Let me run the simulation for 1 second. And let me run this. You can see it's still increasing. Even the capacitor voltage is increasing. But if you see that the simulation, whatever the simulation that we have, whatever this is going to simulate, this whatever the block set they have given, their simulation has already given us the solving. And because of average modeling, our output is not yet settled. So average model is not only the one. There are so many models. You cannot simply average that. But it doesn't mean that your output is not going to attain. If I'm going to give very large time, I think it is 25 seconds. If I give for 25 seconds, let us run the simulation and let us leave that. After some time, it is going to oscillate, and it is going to settle at the steady state value. So it will take long time in this average model. If we have this much disadvantage, then why we are studying this average model? See, I'm getting an accurate model in Simulink block set. In Simulink block set itself, whatever this brown color and blue color, this is a Simulink block set. Here itself, I'm getting the proper value. In average value, I'm getting very wide range of outputs. You can see that it's going to settle somewhere else. So, but why we are going for that? See, this simulating blocks that you can connect and you can test. But in order to test that, for an open loop, it is okay. In order to do closed loop, you need some transfer functions or state space methods to understand that dynamics, and based on that, you're going to give your required output. So based on the transient waveform that we give, they're going to settle at that point. Let it simulate, and I want you to practice this. So along with you, I'll practice the same thing. Control, and I'll just move this here. That's right. Okay, let it simulate on its own. Here I'm going to simulate. Let me take state space. So for the state space, let me take mux. I'll connect it here. I'll take constant. So one, I'll connect it here. I'll take another constant. This I'll connect it here. So which is my VD. Let me take, this is my VDC, which is my 12 volt, something I have given. This is my voltage drop, 0.8. I'm doing simulation along with you, so you can also do the same. I want you to perform this. Then you can use dmux. Connect it. Use a scope. So you can connect the scope to this. Now I need to enter ABC parameters. So I have already given you in the chart box. Let me copy A value. Control C. Here I can copy Control V. And this is my Control C. Control V. This is my C. Control C. Control V. Control C. Control V. Yeah, you can observe that D is also a 4x4 matrix. Both has to be of similar content. You can click apply. Okay. Now I don't have those values, so you have to copy from above. Let me give those values to you. Model properties, callbacks, initial function, Control A, Control C. Okay. Let me give you all the values. Control V. Yeah, I can copy all this. Control C. I've given you in chat box that modified one. You can right click, go to model properties, callbacks, go to initial function. You can paste all the values. Apply. Okay. So what is my first variable? First variable is my inductor current. The second variable is my capacitor voltage. I always prefer white background. Two. I'll take black light. Okay. I'll simulate. So this is how I have got for 10 seconds. Let me run for 25 seconds. If I run for 25, then you can see it is almost settled. If you give them 30, see, if I'm alone plating this, you can see that it is almost settled around 2.4, which is actual output for us. It is somewhere around 2.4, it is going to settle. If you take that capacitor voltage, But if you see that inductor current, it is going to oscillate around 0.8. So this is how you can see the set values there. I mean, they are more appropriate to that. This one is going to take very long time. See, this is my simulation for that. This is my actual DC component, and you can see that my inductor current is going to settle after some time. Maybe after some time it's going to settle. It's almost like you can see that color. Actually, I have very high switching frequency now. So you can see it is almost like 0.85. It is almost settled. If you see that its average, it is somewhere around 0.8. Somewhere it is here. Similarly, you can see that inductor average values. That means the more you go to nonlinear, if you include more and more nonlinear parameters, your state space representation will give you the accurate result. I mean the steady state values. It will give more accurate result with respect to steady state values. I think you got this right. I want you to simulate this. It won't take much time for you. If you do the simulation separately, it will execute very fast. I've got some questions. Any questions on this? Now, actually, after this, we're going to have even better thing. Yes, clear. Okay. Okay, then first let me clear my workspace. Otherwise, my laptop will go very slow. I've run one simulation for 25 seconds. So that's why it will work, execute. It's very slow. Utterly slow, it will work. So this is how you can simulate. Okay. Now this is with nonlinear parameters. And again, the same thing, let us see for boost converter, but I'm not going to tell about the dynamics. I'm just going to tell about the basic boost converter. So this you can try it. VDC, the same thing. When the switch is on, your on equivalent circuit will be like this. This is under steady state. Under steady state, it is going to behave like this. In the beginning, it will have 0 values. Similarly, when it is off, the DC inductor, then this will become forward biased, because inductor large negative potential will be applied. Inductor large positive potential will be applied across this, because inductor does not allow sudden changes in current. It's going to reverse its voltage polarities. So initially, when it is positive, it is going to charge positive and negative here. Initially, it's going to charge positive and negative here. But when the switch is open, as it does not allow sudden changes in current, it's going to reverse this voltage polarity, positive and negative. As this positive is connected to the diode, it will become forward biased and it gets short circuited, and your equivalent circuit will be like this. So this is my on state and off state. And if you see that same, that off state is equivalent to buck converter on state value. Whereas on state, it will have different thing. So in buck converter, now you can see that same equation almost. Let us see buck converter. If you see buck converter 0 minus 1 by L, D by L, like this you can see. Similarly, 0 minus 1 by L, here D won't come because it is an off state, right? So it have different value. It will have minus 1 by D. It will have minus 1 by D. So if I do averaging again, so you will get this equation A, B. So your final state space equation is like this. Now I have got the state space equation of this boost converter. Okay, that we'll see later. Let us simulate this boost converter. Let me give you the values. First, let me comment that. Right click, comment out. If I don't comment that, there might be some common values. Suppose see, I have used IL VC here, and same IL VC also I have used here. If I don't comment that, there will be conflict for this simulation and it will pop up some errors. So let me uncomment this. The same thing, I have done the boost converter. My input is VDC, which is 12. So what is my duty cycle? Duty cycle is again D. I think I have given 0.25. Callbacks. Yeah, my duty cycle is 0.25. That means for boost converter, I think it is 1 by 1 minus D. V naught equal to 1 by 1 minus D V in. So my D is 0.25. That means 1 by 3 by 4. So it is 4 by 3 times of V in. As my V in is 12 volt. So 3/4. My output voltage V naught has to settle at 16 volt. So let us see that. And the same, the state space equations. Let me give you this state functions. Control C. Sorry, that's wrong actually. I'm giving you now. I just got a dash there. So it's easy for you to copy and paste. Don't ignore the state space. If you can understand this, the next consecutive parts will be more interesting. So I've given you all the values. And if you simulate this, let me see the comparison. Still comment. No, it won't be. So this is my ripple content in the output voltage. That might be because as we are having a very large output voltage, so I need to use larger value of capacitance. If I increase my capacitance, so initial function, my C is just 220, right? So 22, I'll make it 10 times, like 220 microfarad, which is the most frequent capacitance I use. And if I simulate this, definitely your ripple is going to reduce. Your ripple almost reduced. You'll have this deviation. Ideally, on an average, you'll have more value, but this MATLAB Simulink block will give a lesser value because of drops considerations here. We have some drop considerations of this one and diodes. Because of this, you're going to create that drop. I'll give you some time. Any queries? Okay. So I think you got that thing right. It hardly takes 5 minutes time for you to simulate this one. I mean, you can simply copy that 12 and I don't need this extra thing. Delete this because now I'm going to use boost converter. Let it be boost converter. So let me copy that thing. Control C, Control V, Control C. I think these don't change. Only D will change. Control C. I. Okay. You can simulate the same. Actually, you're getting a simple straight line probably. This is because I've used a very large time here. You can go for 0.05. Do that, then you might see that increase in values. This is for inductor current. One is for inductor current, which is something 16 by something. As you can see, the average value is 16. You can see that average value is 16. Whereas my inductor current is 16 by 3, which is somewhere some 7 point something, you'll get it. So this is one part. I hope it's not so complex. You have the data and you can do this state space representation. Now, if you have state space, you can find a transfer function. If you have transfer function, you can assess the stability of the converter. And not only the stability of converter, you can do a lot of things. So let us see this one. Is it possible to find the state variables of DC-DC converter in symbolic form? See, what we have done here is, I don't want to save it. Let it be as it is. What we have done here is clear. What we have got here is I'm getting DIL and VC in the form of some, what you call, some waveforms. Here you can see that I'm getting IL and VCs in the form of some waveforms, but I want its equation as a function of duty cycle. That too, I want them in this variables itself, like L, R, and C. I don't want as a single as a normal function of duty cycle. That we can attain in MATLAB by using some SIMS format. So there is something like SIMS. So in this SIMS, you can type R1, R2, and all these things. These two are my equations, which is my DIL by dt. You can see this equation. And this is my dVC by dt. You can see this my equation. Let me increase the node size. I think it's but you are going to say smaller roughly. Okay. Okay, that's fine. Now I want that, see this equation 1 and equation 2. These two are my state space equations actually. If you just see above, these two are my state space equations. This is for boost converter. You can see for buck converter. So 0 minus 1 by L like this. But if you take the dynamics of the system, so this is how minus D into R1 minus of 1 minus D into R2. This entire term is my IL. If you see here, minus D into R1 into IL minus 1 minus D into R2 into IL, the same equation I have written here. So the same equation I have written here. So this is like DIL by dt. And what about this? This is something like dVC by dt. So these two I have got, and you remember, for a given DC-DC converter, on an average cycle, the average voltage across the inductor is 0. So if you take integral VL over the time period Ts, 0 to Ts, over the time period 0 to Ts, over the time period 0 to Ts, if you integrate inductor voltage dTs, it has to be 0. Similarly, if you take over a cycle 0 to Ts, the capacitor current IC dTs, again it has to be 0, isn't it? Now this d and 1 minus d, this is the average representation of my network. I'll use a solve function. I want this equation 1 and equation 2 to be solved. And what parameters do I need? Among all this, see R1, everything, even IL, they're all variables only. I can tell you what is this sims function. Suppose I'm writing like A is equal to R by 2. Let us write simply like this. It is saying that it don't know R. Then let me write sim of R. Let me define this R as a variable. As you can see, in workspace, my R is saved as a variable. Now you can write A equal to R by 2. What happens is now it is not going to return that value. It is going to return that a variable format. So this is what I want in MATLAB. It's actually quite larger. Okay. So this is how I can do. So let us open some script, new script or any live script, whatever it is. If I open that script, you can copy this content, Control C, Control V, and I'll copy the same thing to you, Control C, Control V. Yeah, I think you got everything. See, now I just want VL and IC in terms of all this R1, R2, R in terms of duty cycle as a function of duty cycle. But it shouldn't have any other parameters, like IL should not be associated with any other state variables. Like it should not have VC and it should not have any other. Suppose I have only two state variables here. So IL should be a function of other things other than VC. Similarly, VC should be a function of other things other than IL. So in the result, when I'm solving these two equations, so I'm going to take IL and VC are my required parameters. So if you run this simulation, you have to first save it. Parameter identification. Parameter identity. Let me simulate this. You can see that I have obtained my IL and VC like this. If you can see, this is my dVin minus Vd plus dVd, everything into R power 5 plus 3 RC, something like this. So this is my inductor voltage, sorry, inductor current. So I've obtained in variable. So once you obtain in variable, you can give whatever the value that you want and you can find that. Suppose this inductor current as a function of duty cycle, you can plot your inductor current with respect to duty cycle because you have that equation. You can give all the other values, like you can give Vin, you can give R, RC, every other values you can give. Instead of sims, you can give their actual values except IL and VC, and you can write that IL equation like this. And you can vary duty cycle D, like D is equal to 0 is to 0.001 is to 1. So from you can take this and you can start varying that and you can plot between IL and D. Then you'll get your actual response. This I'm not going to tell. You can find it on your own. Because I have given this part, I told you how to find your inductor current as a function of duty cycle. Similarly, you can find VC also as a function of duty cycle. Okay, this is how you can find it. Now you know you can find any parameter IL or VC, any parameter. See, as I said, if I know the state space equation, state space variable format, you can determine your inductor current or a capacitor voltage as a function of duty cycle. Once you can find, it is not just for buck converter, any converters that you take its equivalent representation. and you want to find across your respective passive element components, like whatever the state variable components that you have, that you can find it instead of finding as a function of time, but you want it as a function of what you call as a function of duty cycle. So this will give you a specific value of inductor current for a given duty cycle. So this is what we want. And using the simplify, you are going to get a format like this, like your answer. This is your answer for inductor current. This is your answer for capacitor voltage. So this is one format. Now I know how to find my inductor current and capacitor voltage. The thing is, I want to find the transfer function from state space variable in symbolic form only. So let us see that. Go to presentation. So this is my state space variable format. So you're going to get it in variable format only, your inductor current and capacitor voltage. There's one form. Now you just want to find the transfer function in variable format. See, I have this transfer function 2 as something like this. So there is something called TF function. You can find the transfer function. But if I want in symbolic format, let us see whether it is possible or not. Before that, let us open a live script. New live script. So let me take num equal to 1 space 2 and 10 equal to 1 space 2 space 3, something whatever. And you are going to find your state space h equal to TF of num comma then you can run this. So your h is going to come. Yeah, so this team of num comma then. It's taking so much time. Yeah, this is my transfer function. But let me define sims of a b or something like this, and let me define here as a into b, and let me define as r. And if you run this, it cannot recognize ABC. Sorry, it is sims, right? So if I run this, it cannot recognize. Means it cannot generate this form as a transfer function. That means whatever the variable state-based variable format that I have, you cannot get that in variable format. Why we need variable format means, in papers, you cannot directly place the value. If you can find that equation, you cannot normally find this equation, whatever the equation that we have, you cannot simply solve it because it has so many variables. In order to solve it, it will take so much time for you. But using this result and solve function, and by using the solve function, MATLAB, even for a variable format, you can identify your system. But same thing, I want to find in variable system. Normally, you can use transfer function to find the transfer function. But if you have this symbolic format, this transfer function is going to obtain. Then how we can do this? Let us see. So this is my transfer function. Suppose same, I have my state space, and this is my state space, and you have used SS function to find the state space. Like it is going to give A, B, C, D. If you give this format, then if you use SS form, SS syntax, like we have used TF here, like we have used TF here, SS is also one inherent syntax to find the state space representation. So if you give SS, then you can find it. But instead of a normal values, if I have symbolic representation, even SS command is not going to work. That means this SS and TF will fail to get the symbolic representation. Can you get it? I think you get it. You don't know why we need this. So in any papers, they may represent like IL as a function of duty cycle, or VC as a function of duty cycle, they may have presented, but it is difficult for you to manually solve it. When you have the flexibility to solve in MATLAB, why to go for that? You can do it here itself. Okay. Similarly, you have the state space representation. We know as we have state space representation, SS is not going to work, is not going to take the symbolic format, and even TF is not going to take the symbolic format. TF is not going to take the symbolic format. Then there is one way you can still find the symbolic format representation. As most of you know this, approve, yes. We know x dot equal to a x plus b u and y equal to c x, actually it is very slow, plus d u. We know this equation. From this, what we can find? We can find transfer function. Your transfer function is nothing but, a lot of people know, c into si minus a whole inverse into b plus d. I think you know the transfer function format, right? If you have the state space equation of this format, you know we can create the state space in symbolic form or equation form we can write. Then your transfer function is simply c into si minus a whole inverse into b plus d. You will get it in variable format. For this, let us go for it. Any queries? No, no queries. I think you're not understanding what I'm saying. You'll understand when I go for it. SS2TF. Now assume that I have A1, A2, something like this. This is my A matrix, B matrix, C matrix, D matrix. So I'll define a variable phi, which is inverse of S. If you see S here, again I have defined S as a symbolic form. So S I of 3 is an equivalent of I matrix, identity matrix of 3 by 3 minus A. A I have already defined. It has some constant values and it has some variable forms. Now what is my transfer function? It is simply C into phi, which is the inverse form of that, into B plus D. So let us run this. Now you can see that my transfer function, as I have only, okay, it's a 3 by 3 matrix, right? So I'll get S cube. So my transfer function is like this. H is equal to, you're getting this equation. You can see this, right? So once you know this, you can directly place it as a result. So you just have to write this format. You have to define. So let us do for our network. Even I didn't do that. Let us do for that. This is for DC-DC boost converter 00 minus 1 by RC. So let me define. Okay, let us take this one itself. Let us copy this equation and control C. SS2TF. Control V. In the state space. Copy this, control C. This is actually very useful that I'm telling you. The paper review commenters, they specifically ask this content. Not this. I have to take this. Sims. I think Sims we are already written, right? Yeah. Now SS to DF, we have to define A, B, C, D, and phi this one. Control C. Control V. Now you have to define what is your A. I think we have already written this somewhere here, not in this one. Let me open this simulation now. Converter. Just wait for a few minutes. Yeah, I think the time is going up, but I'll make it fast. Don't worry. Still loading. Yeah, I think I have my equations here. So this is my A, Control C. So that I'll copy my A here. Control V, semicolon, circle. And my B matrix. This is my B, Control C. Okay, let us do the Control V. Actually, we have to change, like instead of capital D, we have to make it small d. The notations are different here. I'll make this to comment. This is my B. And I want C. Control C. This is my C. Control V. My D matrix. Control C. Control V. Any queries? No, right? Yeah. I just want to find my H. So actually it is small d. Small d I have mentioned. I don't want ILVC because that's not my desired things. ILVC, whereas my D, R1 is okay, R2 is okay, capital R, RC, it is my RL. Yeah, I have to write that equation also. You have to right click, model properties, callbacks, initial function. These two, Control C. Okay. Control V. I think we may get more complexities here. Okay, let's go for this Control R. For this itself, we'll go. We'll try to simulate whether we can do it or not. SS2 TF symbolic unrecognized function S. Yeah, I have to define S also here. Array sizes must match. It's actually 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. Everything is proper, right? So 1, 2, 3, 4, 1, 2, 3, 4. Okay, it should be 2. It should be a 2 by 2 matrix. Thank God. So this is my transfer function actually. So if you see that, it's going to give very large value because I have more parameters here. So R2, everything you can see. It's just like a bigger matrix. You're going to get this function. But even if you get this, it's not a big thing for you to solve because it is actually solving this one and it is giving you the direct thing as a transfer function. So once you get the transfer function, I think it is easy for you to apply any analysis, whether tuning parameters or anything. It is not a big thing for you to find that. Any query? So I told you how to do this, what do you call, how to find the transfer function in symbolic form. If you don't want symbolic form, you can directly give this. Say I want only as a function of duty cycle, then you can define, you can delete that. Whatever all these things, you can delete them and you can define instead of R1, you can make it some value 0.03. Like if you give all these normal values, you will get your transfer function as a function of what you call duty cycle. I mean, as a function of duty cycle. So let us make it something 0.3. So let me write minus 0.3 or whatever it is. So R1 RC 0.03 R 0.03 R1 0.03 1 0.03. So everything is just duty cycle. You can run it, then you'll get a simple equation. Still it is point big. Yeah, because of I have used these values. These values might not be of that value. That is why you're getting a bigger complex one. So this is how you can solve it. But once you get it, it's not a big thing for you to understand that. Even you can manually solve that. If you can get this, you can manually solve. But in order to get this, again, it is a bit tedious task. So once you can, your burden is reduced a bit. That's what I can say. Any queries do you have? No, sir. Everything you are teaching clearly. Thank you. If you have any other queries, you can ask for that. In tomorrow's session, we'll start with solar PV systems. I don't know whether it's like you don't care or you don't, it's not your cup of tea or you got everything. I don't know. And the first time you're getting everything, that's what I was wondered. To understand this concept for me, it took so much time. Where it is useful, sir, if someone asked you to write the transfer function, so if they ask you to write IL, so your inductor current to output voltage transfer function like that, if they ask you, then using this function, you can find the transfer function. AC/AC converters, actually for AC/AC converters, I thought of presenting the basic mode, not like complex closed loop systems. So I just skip that because it's just a basic mode. If you want that, then I'll involve in the later session. Do you want it, sir? Sorry, sir. This state space model is not a nonlinear model. Where you can say that it is a nonlinear model means, if you see, okay, sir, I'll see that AC/AC converters. Yes, I didn't understand it by myself. Now it is clear. Okay, thank you. See, what you can say, when you can say that the state space is not nonlinear. See, here x is something, x dot is equal to ax plus bu. Suppose instead of just I've got directly x. If I get x1 and x2 product, then how can you do that? Then it is nonlinear, right? Here I've got an individual form, like x1 I've got separately, x2 I've got separately. So here it is like linearized form only I have mentioned. Yes, there is one more non-linear format that I have not mentioned here. The boost converter and all, they will come with non-linear forms. Only buck will come with linear mode. For non-linear mode, you have to again do manipulations to that into a linear conversion. Then you can do that analysis. Okay. So this is a linear form only. You can see that it is just directly x or x1, x2. You're not getting any non-linear form. Any other queries? Yeah, I know that you will get that query. In journals only, they will ask you. I mean, even if you want to find the transfer function between one after the other, like even with respect to duty cycle, if you want to find, yes, you can do that. But you have to modify this state space form based on your duty cycle. So once you do that, you have that format. If you place it, then it is going to give with respect to duty cycle. And whatever the analysis that I have done, this is the average model. This is not small signal model. And small signal model, it is again a different method. There you are going to consider everything like instead of dl by dt, small increment in dl by dt they will consider. So small signal model will give you more accurate. Like in the simulations we have seen, right? Here in an average model, I have got my inductor current somewhere very far. But if you do small signal model, you'll get a bit more faster. So there are different models. That is also an average model. But the small signal model will, because of its small increments, it is going to work more clearly. That is one form of methodology. You can search for its papers as small signal modeling of DC-DC converters. This is average modeling. Small signal modeling can also be an average, but you are not going to directly consider dIL by dt like this. You are not going to consider dIL by dt on dVc by dt. Change in dIL by dt and change in dVc by dt you are going to consider, and there you will get that nonlinear form. At that nonlinear form, you are going to approximate. You want to see that in the next consecutive sessions. How to design a controller for this using. Yes, we are going to see that in the next consecutive classes. Once you get the transfer function, you can do that control. There is one direct tool that we'll see in the next consecutive classes. Any other queries? Okay, I think the time is too much. Thanks for your patience. Somewhere I have explained the concept very fast. I can tell you till boost converter, but BLDC motor drive is again a different concept. Because BLDC motor, it again requires an inverter. I'll discuss perturb and observe method or incremental conductance method and basic solar PV systems with a boost converter. Model predictive control. I'll see to that, sir. Why you want only model predictive control? Don't you have an existing model? If you don't have an existing model, then you can go for model predictive control. Yeah, we'll see that, sir. I think I'm not going to involve model predictive control. I'll just teach one thing. So I have to practice. If I can get that, then I'll give you that. I'll just take one small example and I'll try to deploy that model predictive control at the time. So BLDC motors is again a different concept. Feeding a DC motor, you cannot simply feed that. You have to use DC voltage regulation. There are so many complexities in between. So I'll just go till DC-DC converter alone. For the inverter concepts are again different. So inverter fed motors, everything is again a different concept. And that too, when you're feeling with solar PV, there is a huge, you'll face a lot of hectic problems with solvers. So you have to linearize that. Everything you have to write in the form of equations or in the state space format, and you have to do that. Then you may get something properly. Please suggest some sources for better understanding. Actually, these are being solved by our colleagues. We practiced it and we're just presenting it to you. I mean, one person know one concept, the other person know the other concept. We'll share among ourselves and we are presenting it to you now. You have so many resources. You can directly type in internet. If you can get it, you can go for it. If possible, I'll try to put references here. Because I'm not teaching you some complex things here. These are just the basic notes. I was just explaining how you can deploy that in MATLAB. That is the only thing I'm presenting. I don't think these are very complex. These are just the basic equations. Okay. Thank you for that. Then we'll see in the tomorrow session. Jai Hind.